Am I audible, sir?
Yes, sir. Now you are audible and visible also.
Oh, thank you.
Very good evening.
Good evening, sir.
So let me give you a first introduction, then we can start our formal session. Dear participant, now today's second session we are starting. Before starting the second session and hand over to the Dr. Kamalesh Joshi, let me introduce him. Dr. Kamalesh Joshi is an assistant professor in Department of Mechanical and Aerospace Engineering at the Institute of Infrastructure Technology Research and Management, Ahmedabad. He holds his PhD degree in manufacturing from IIT Bombay. He has done his MTech from IIT Roorkee in metallurgy. He has expertise on non-conventional machining processes, microstructure characterization, thermal modeling, solar cells, and anti-corrosion coatings, with a particular focus on wire EDM applications for material like silicon wafer and silicon carbide. He is also guiding the certain PhD student and many MTech students already he has guided. Right now he is also handling the 3 to 4 research projects also. So with this short and brief introduction, I would like to invite Dr. Kamlesh Joshi to deliver the talk and hand overing the session to you, sir.
Thank you, Dr. Piyush sir, for inviting me in this faculty development program. Namaskar, everyone. I'm Kamlesh Joshi, and the sir has already given a long introduction of me. I want to add that sir told that his area of expertise. I want to add, it is not my area of expertise. It is my area of interest. I am not expert till now. I will try to become expert in some of the field. And I had a chance to listen and join the meeting and listen to Dr. Anish Gandhi's talk for last 10 minutes, and it was a very wonderful talk. And from the comments also we can see that people have liked it so much. I will try to match up with the content and quality with the previous experts which have delivered the talk. Now I am going to share my screen. Let me see. I will switch off my camera so that the video will not interrupt in between. So it is visible? The
Yes.
screen? Okay. Thank you. Namaskar, everyone. I welcome you all to the third day and second session of the recent developments in micro nano machining in contexts of Industry 4.0. And I am Kamlesh Joshi, and the topic of my talk is nanostructuring for biomedical application on magnesium alloys. Currently, I am working as an assistant professor in the Department of Mechanical and Aerospace Engineering at Institute of Infrastructure Technology Research and Management, IITRAM, Ahmedabad. And along with this, I am also working as a TARE fellow at Machine Tools Lab at IIT Bombay. And first, I want to briefly introduce the department at which I am currently working. So the Department of Mechanical Engineering got its inception in the year 2014. With around 96 students, we enroll in first year in our UG program, BTech program, and we have around 20 students intake at the master's level. And we have program both BTech Mechanical Engineering, MTech Mechanical Engineering, and PhD. Along with the BTech program, we offer honors program. So you can choose extra subjects over the required credit to get the BTech and get a degree with honors. At the same time, we have several minor programs. So Department of Mechanical Engineering offers minor in drone technology, and so students have to go to some 3 to 4 subjects related to the drone technology. If he or she clears the subject, then they gets a degree in minor along with the regular degree. Apart from this, we also offer some micro specialization courses. So currently we are running 3 micro specialization courses along with the regular courses of honors, minors, and BTech program. We have first these intelligent human robot interactions. Second one is the nanotechnology and functional nanocomposites. And the last one is industrial safety engineering and management. In our department, we have a total of 11 faculties currently working, and we have around 10 lab staffs and several labs. These are the faculty members and their profiles in our department. The faculty members are from various IITs, NITs, BITS, and from outside also. And till now, our department has organized 7 international conferences. Around 26 workshop and short-term training programs has been organized. 10 PhDs has been awarded, and 17 research projects has been completed. We have around more than 600 publications in reputed journals and conferences, with around more than 11,000 citations and 37 patents. Our department has completely combinedly completed around 155 lakhs 155 lakhs of project, and currently we are undergoing a project which costs around 542 lakhs, and several projects are still under consideration. This is a brief list of the labs or undergraduate labs we have at our institute, with heat and mass transfer to the fluid mechanics lab, all the basics lab we have. Apart from this basics lab, we have some state-of-the-art facilities with us, including the cryogenic machining setup, Viridium setup, electrostatic minimum quality lubrication setup, air conditioning simulator is there, wind tunnel is there, rotational molding setup for making the plastic products is there, photoelastic experiment using polyscope, and we have also a high speed computational facility for simulation with several software packages like ANSYS, MATLAB, and Abacus. And we have in the field of aerospace, we have aerodynamics trainer, axial flow gas turbine test rig, axial flow gas turbine test rig is there. So all these facilities are open to all the researchers. All can come and join and work with IITRAM at our institute. These are some of the sectors where our students get placed. Some list of government sector, PSUs, and these are some of the universities where our students go for the higher studies. So this was a brief introduction to our department. Now the work which I will be presenting today is done with the collaboration of IIT Bombay. So here it shows that we have this facility of diamond turning machine at IIT Bombay. and the associated professor here is Professor Rakesh Mote. And the facility developed is ultra precision manufacturing facility, which is funded by the Ministry of Education under the Institute of Eminence program. Along with this, some of other facilities which we are using is the tools makers microscope is there, white light interferometer is there, Alicona microscope is there, some optical tensiometer is there to measure the contact angle of the drop. Let's say if we have a surface and we put some drop over the surface, then it can measure the angle of contact made by the solid surface and the liquid surface. Here you can see if the angle is something like this, which is acute angle, it looks like something like this, which is less than 90°. So we can say that the surfaces are hydrophilic surfaces, means the surfaces are wetting type of surfaces, and the liquid will wet the surface. If the angle goes beyond 90°, the surface is called hydrophobic surface, and it become slightly non-wetting type of surfaces. And if we are further able to increase this angle by more than 150°, then the surfaces are known as super hydrophobic surfaces, and the materials are super hydrophobic materials. So this is what the facilities we have at IIT Bombay. Now, as per the theme of the program, I first want to give a brief about what is different type of manufacturing in the terms of domain. So we can see here we have some regular manufacturing here, which is conventional using lathe machine, milling machine. That is known as macro manufacturing. Here the part size or the feature size varies from 1 mm to 1 meters. Then if we are able to reduce the feature size to hundreds of nanometers to some of the micrometers range, the manufacturing is known as micro manufacturing. We have list of machining and manufacturing processes which are classified into macro manufacturing and micro manufacturing. We'll see the processes which link these two processes, which are macro manufacturing and micro manufacturing, are termed as meso manufacturing. And the processes which goes beyond micro manufacturing, whose feature size goes beyond say tens of nanometers up to the angstrom level, those type of processes comes under nano manufacturing processes. Here we have some of the features or some of the components shown here. So you can see small silicon nitride gears are there, and the scale can be seen as 1 micrometer. Let me see if we can have some laser point. Okay, so you can see the scale is 1 micrometer. So these are very small size gears. Similarly, we have some of the circuits are there, some flow channels are there, some grids are there. Here you can see some of the shapes which are formed, some of the other things like micro grippers. So from the scale size, you can see that these are made at very small scale, which comes under the nano manufacturing. So classification wise, we can say that the processes which comes under conventional machining and have the large components with them are the macro machining processes. And then if we reduce the size to millimeters in the terms of depth of cut, miniaturized products are there and mid-sized structures are there, then the process can be termed as meso machining. Then further, if the machining depth of cuts are in micrometer range, for example, micro turning, micro milling, micro electrical mechanical systems are there, then the processes are micro machining process. And if we further reduce the processes in the sub nanometer depths of cut, and we are machining in the atomic scale, means we are machining grain to grain, and the cutting radius of the tool is in the range of grain size, then we will say that it is a nano machining process, and we can make the ultra precision components from the nano machining processes. The processes can be classified in two ways. One is the microsystem technologies, which are generally employed to produce the micro electromechanical systems, and another one is microengineering technologies, which are processes related to mechanical machining. Okay, so here in MST processes, where we produce micro electromechanical systems, we have processes like photolithography, electroplating is there, micro electroforming is there, chemical etching is there, where we don't use the either conventional machining forces to remove the material or the unconventional modes of material removal. Then the processes will be classified as the microsystem technologies. And here, when the processes uses the shear deformation to get the shape, then we call those processes the microengineering technologies. The classification is like micro turning, cutting, micro milling, grinding, and some non-conventional machining process like laser machining is there, micro EDM or EDM is there, focused ion beam machining is there. So these processes comes under the mechanical machining processes. We'll see in brief one by one what are the capabilities of these processes and what parts can be made. So first, the schematic shows the micro cutting process. Here we can see a tool is there whose the rack angle is um, negative, and the chip formation is happening there, and the cutting is happening in this direction. So you can see the tool can be seen as a sharp tool. Okay, so this is a macro machining process, but when we cut a grain to grain in micro machining or nano machining process, we cannot have tool. If you magnify the tool, you can see that the tool is not sharp as it is seen in the figure. Okay, so tool will have some edge radius, maybe in the range of 0.2 mm, 0.5 mm in this range. So this edge radius will be there, and due to this edge radius, different type of mechanism will come into play. Either will be the shear deformation taking place, or maybe extrusion type of process taking place, or maybe simply plowing taking place. So these phenomena comes into picture when we do the micro cutting process. So the depth of cut in conventional macro machining is significantly large than the radius of cutting tool. So this is the radius of cutting tool, and the depth of cut is this depth is sufficiently large in the conventional macro cutting, and the macro chip formation models are created with the assumptions that the cutting tool can be completely can completely remove the surface material. And but in the micro cutting, the depth of cut is close to the radius of cutting tool. So if say the depth of cut we want very less, so we can keep in the range of the edge radius of the tool. Here some of the features are there which we can see. In micro cutting, we can produce the rotational convex shape with high aspect ratio. So this is the needle, and you can see the diameter of needle is in the range of 5 micrometer, and the surface roughness which can be achieved using this is the in the range of 0.05 to 0.3 micrometer. Similarly, a plastic molded part is there, where we can see a slit is there, and the slit is also in this range, and the surface finish is less than 10 micrometer nanometer. So this is from the micro milling. The references are given. Holes drilling can be done using the micro drilling process. The size of hole is again in the range of 5 micrometer, and we can make some shapes, convex and concave shapes of hard brittle material is there. You can see the structure width is in the range of 13 micrometer, and the surface roughness is in 10 nanometer range. If we want to achieve this type of surfaces, we need cutting tools of similar type of dimensions. So you can see these are the cutting tools which are used for the micro cutting processes, and to achieve the dimension of these cutting tools, a special type of process which is focused ion beam process is used. So you can see this tool, it has two cutting edges, and in this tool it has four cutting edges, and in this tool it has around five cutting edges. Similarly, the tools can be made from another process which is electric electro EDM process, electric discharge machining. The whole size which is produced from this tool diameter is less than 2.5 micrometer, and the whole size which can be produced from this tool is around 5 micrometer, and this is the slit size which is produced from this tool. So the tool manufacturing again is one of the important aspect. Micro EDM is again one of the advancement in the conventional EDM process, where we can get the wall thickness of the material in the micrometers and nanometers range. You can see some of the examples. A shape edge microstructure array is there. A high aspect ratio pillars array is shown here, and a micro compressor machined by EDM process is shown in this. Similarly, a micro electrode machined by micro wire EDM is shown here. So these are some of the difficult to achieve shapes which we can achieve from the machining process. Another process is laser micro machining. The laser is having a vast capability in its own, and it can produce various type of difficult to achieve shapes, like these are through holes of array, and you can see we can achieve the arrays required through the laser machining. This is the honeycomb type of microstructure which we can make, and this is a micro spinneret which is in the size of hundreds of micrometer, and these are some of the cone like protrusions fabricated by laser micro machining. Okay, so laser micro machining again can be done in two ways. One is the percussion type of laser drilling is there, where the laser beam is focused on one area, and then it keep on removing the material throughout the depth. You can see the depth, high depth can be achieved. The problem here in this process is that we get the diameter which is tapered from top to bottom. Another way is to trepanning type of process, where we rotate the beam from corners to edge and remove the material. So the whole diameters which are achieved are relatively more as compared with the precussion method, but here the tapering is not an issue. So if we want to have a uniform type of hole with uniform diameter, you can use this type of process. And the last one process which I want to discuss is the focused ion beam type of process. Here we have the ions of high energy focused on the substrate, and these higher energy ions bombard on the subject, which causes the localized heating on the subject. It removes the material in the sputtering form and creates the hole by removing the material. You can see some of the specimen here. One of the use of this FIB process is to prepare the transmission electron microscopy samples. In this example, you can see the molybdenum alloy micropillars are made, and a monocrystal diamond micro tool is fabricated using focused ion beam micro milling. So these tools then again can be used in the diamond turning process to create the required features. Now coming to the theme of the top, that we want to produce the micro features on the magnesium alloys. So before going to the magnesium alloys, we will see what are the orthopedic and dental implants. So as we are already knowing that the orthopedic implants uh, are the metallic or alloy parts which are inserted into the body of the patient to get the desired strength of a particular part. Okay, the common materials which are used are stainless steel and titanium. So what happened that some of the cases when we put the part after the healing, the tissue growth happens in the part, and we have to remove the implanted part using a secondary surgery, such as if we are putting some screws, plates or rods in the bones, and after some time if our bones get healed, what we have to perform, we have to remove those parts using a secondary surgery. Okay, so these implants are typically used in orthopedic surgeries such as fracture repair or joint replacement, and fracture fixation is routinely performed with the use of metal implants. Why? To restore the anatomical alignment and to allow the enhanced functional outcomes. Okay, so kya material? So the material which are used generally are the stainless steel, titanium, particularly pure titanium and titanium 5, a TEL64 titanium based alloys are used. You can see here orthodontic implant example is shown. So first drilling is being done, and then we are putting some screws inside the gums, and once the screw has been inserted, it'll develop the tissues and strength around the system, and then the tissue, the screw will be removed, and then the required tooth will be inserted in this place. Okay, so this is one of the example. Uh, People have used or tried the magnesium based biodegradable temporary implants in the body. So why we are choosing magnesium over the already successful materials like titanium and stainless steel? Because they have emerged as promising alternative to the traditional metallic implants due to their biocompatibility, biodegradability, and acceptable mechanical property. So they have this property that once they are inserted inside a patient's body and the body got heals, we are not required to perform a secondary surgery. They get absorbed in the body, and hence they reduces the need of removal due to secondary surgery. And as we are not doing the secondary surgery, the potential for the long-term complications has been avoided. So these type of implants are used in orthopedics, dentistry, cardiology, and some other medical fields. Some of the examples are shown here. These are the orthopedic devices which are made from the magnesium alloys. This is one of the tightening screw as we have seen in the previous slide. And a cardiovascular stunt is shown here in this picture, which is used to expand the blood arteries. If there is some blockages there, the doctor will insert this type of stunt in the body, and then they will expand the artery and help to flow of the blood inside the body. Okay, similar others, you can see there are various type of stunts made from the magnesium alloys and various type of other orthopedic implants which are made using the magnesium alloys. So magnesium alloys are very good choice for the implants. So what are the main properties due to which they have become a competitive material for the titanium and stainless steel? So first thing is that their mechanical properties are similar to the bone material. And then these properties can again be tailored using the alloying elements like aluminum, zinc, So these alloying elements, what they will do, they will enhance the strength and reduce the corrosion forming impurities like iron and nickel. The second advantage of magnesium and its alloys are that they have a very good biocompatibility with the body. So magnesium has similar mechanical properties as human bones. However, gradually they are absorbed by the body, and magnesium is one of the required iron or mineral in the body. So if it is gets dissolved in the body or gets mixed with the blood line, it does not harm the body. Therefore, if it gets absorbed in the body, it eliminates the needs of secondary surgery, which is generally used in the titanium implants. Third thing is that it is having a very good biodegradation. So biodegradation refers to the process by which a material breaks down over time in the physiological environment. Physiological environment like the we have blood in our body, and the blood will create a physiological environment and get metabolized by excreted in the body. Okay, so here is an example which can be seen that a screw is there. If we put this screw in a physiological environment, after 1 month, it will get a degradation which can be seen in this picture. Further, after 4 months, the screw got degraded in this manner, and after 7 months, the screw got degraded at this point completely. Okay. Fourth and foremost, the most important thing is the osseointegration. So osseointegration is the bioactivity, means it helps to grow the tissue and it protects the growth of tissue over the implant. Okay, so what happens that it creates an apatite layer which is composed of inorganic compounds like calcium and phosphates. So what is happening, let's say we have a magnesium material with us, and it is in contact with our bloodstream or other physiological environment. Due to the reaction with this media, it will generate the magnesium ions. When these magnesium ions are generated, they interact with the body media and make the magnesium hydroxide component. Further, this magnesium hydroxide combined with the calcium ions and phosphate ions in the blood and make a layer which is known as apatite layer. This apatite layer, which can be seen here in the brown color, covers the part which is our implant, and a tissue growth can happen over this. So this is a type of passive layer which stops the further degradation of magnesium alloy or implant, and then the tissue growth, it helps in the production of the tissue over the material. Okay, so here is a summary why we have chosen the magnesium and magnesium alloys for the medical implants. First, that they have the natural biodegradation capacity due to their susceptibility to corrosion in aqueous solutions, especially if they are contained in the chloride ions as compared to the irons and iron in its alloys. Magnesium has excellent biocompatibility, and these ions are released in the bloodstream, which are used in natural metabolism and does not have any toxic effect or side effect on the body. Its mechanical properties like modulus of elasticity matches with the natural bone modulus of elasticity, as compared with the other materials like stainless steel, which is having very high modulus of elasticity, cobalt based materials and titanium based materials. So these three materials, you can see the modulus of elasticity is very high. However, the magnesium is having a comparable range with the bone material. They are also exceptionally light material. The density lies around 1 to 2 gram per centimeter cube, which is very lower than the titanium alloys, which is around 3 to 4 times of the magnesium alloy. And this density is closer to the natural bone, which leads to the lighter implants compared to other metallic biomaterials. So here we have seen these are the three steps of the biodegradation. First, the surface oxidation happens. So magnesium blade implants, when they are exposed to the biological environment, develop a thin oxide layer as seen in the previous slide. And these oxide layers tend to serve as a protective layer and further prevents further corrosion and degradation of magnesium implant. In the second stage, the corrosion starts. The magnesium implants start to corrode actively in the biological medium by the electrochemical reaction. So the anodic and cathodic reactions are shown here. Magnesium first disintegrate in the form of magnesium ion and electrons. When these magnesium ions and electrons interact with water molecule, at cathode, hydrogen gas evolution take place, and the product is magnesium hydroxide, which is a biocompatible type of material. In the third stage, a dissolution take place, where the magnesium implant is gradually dissolved in the body fluids, and the released magnesium ions are transported away in the body fluids, and then they are excreted through our metabolic system. So apart from these advantages, there are some issues in the use of magnesium as the bioabsorbable material. First, its rapid corrosion and degradation is one of the issue which causes the formation of magnesium oxides quickly in the body. This rapid degradation can lead to premature loss of mechanical integrity before the tissue has been fully healed. Another problem is the hydrogen gas evolution during corrosion, which causes gas pockets, tissues necrosis, and delayed healing. So this hydrogen gas evolution is another problem, and it has low strength and fatigue resistance, which can be problematic for load bearing application. If the application is of static type of loading, then there is no problem. But if the application is of dynamic nature, then due to its lower fatigue resistance, it may cause some problem. So these problems can be overcome by various ways. One of the ways is to add the alloying elements in the magnesium. So the addition of alloying elements such as aluminum, magnesium, zinc, zirconium, calcium, and other rare earth elements enhances the corrosion resistance of magnesium based implants and effectively control the biodegradation. Okay, so however, we cannot excessively use these alloying elements because they can have the adverse effect on the body. For example, the addition of aluminum after a certain limit can have a risk of Alzheimer's disease. Another way to improve the biodegradation is by surface modification. So we can improve the properties of the implant surface to control the biodegradation or corrosion rate. One of the ways is to coat them with biocompatible material like hydroxyapatite coating and calcium phosphate coatings, which enhances the corrosion resistance and promotes bone growth and tissue integration. This is one of the highly used technique on the magnesium materials. Another way is to control the surface roughness. So controlling the surface roughness improves the cell adhesion and tissue growth, which helps in the osseointegration, but excessive roughness has adverse effect and can accelerate the corrosion. So we have to carefully play with the factor which is surface roughness, because on one hand it improves the tissue growth on the implant, on the other hand it accelerates the corrosion. We can do anodizing to add the protective layer over the surface. Another way is to have these plasma sprays to create a surface roughness, a rough surface, and deposit compatible material to enhance the corrosion resistance and prevent rapid degradation. So these are some of the ways which can be used to improve the biodegradation of magnesium materials. Here a list has been shown which shows various type of magnesium alloys which can be used for the bio implant material. First is the pure magnesium. However, the dissociation rate in the pure magnesium is very high. Another one is the AZ31B, AZ63B, AZ91B, and they vary in the aluminum composition inside them. Apart from this, there are several other materials which are yet to be explored for the biomedical application. Now in this work, what we are focusing to change the surface of the material to improve the roughness parameters of the material and improve the hydrophobicity of the material. In order to do so, we can use several methods. Laser machining is one of the way which people have already tried. We have this facility of diamond turning process which has the ability to produce the micro features or nano level features on the surface, and those nano level features can affect the corrosion behavior of the material. So first we'll see what is this diamond turning process. So diamond turning process is similar to our conventional lathe machining process. Only thing is that the tool size is very controlled, and it is a ultra precision machining process which is used for achieving a surface roughness in the range of nanometers on various difficult to machine materials without affecting the accuracy of the components. The famous materials which are used on diamond turning process is aluminum. The brittle material like silicon carbide are also usually investigated on this diamond turning process. So you can see a schematic of the process is shown here. Here we have a tool post over which a diamond tool is mounted. Here we have a workpiece chuck. Here we have mounted the workpiece, and then we have some of the axis. One axis is this x-axis. So this x-axis can move the workpiece parallel to this axis. Then it can have the y-axis, which can increase the vertical level of the workpiece. Then we have this z-axis, which is used to provide the depth of cut inside the material. And then we can have this rotational axis, which is known as the c-axis. So here in this diagram, three axes are shown: x-axis, z-axis, and c-axis. Apart from these three axes, we can have y-axis. So it will become a four-axis machining system. And then we can have a b-axis on which we can rotate our tool to some angle also. So this tool post can be rotated to some angle. So it will become a five-axis machining system. So here we can see c-axis rotates in the rotational clockwise or counterclockwise way, and this tool post is given a depth of cut parallel to z-axis, and then it is given feed in the direction of x-axis. So in this way, we can create the features on the material. One important thing is that the z-axis can be given some vibrations of some magnitude. Based on the amplitude of these vibrations, we classify the process in slow tool servo process and fast tool servo process. We'll have a look on the slow tool servo process and fast tool servo process. First, what is a slow tool servo process? In this, the z-axis, the tool post is vibrated parallel to this z-axis. So slow tool servo turning is a process for machining precision and complicated surfaces. It relies on the tool slide and it's include the spindle c-axis motion and up, and the motion of this vibration is synchronized with this c motion. We can have a video to see the slow to servo process. So a diamond turning of a 10 millimeters tilted flat is shown here in the demo. You can see the amplitude of vibrations are slow and they are synchronized with the C motion of the workpiece. A toric form is machined in this example. A large off-axis paraboloid is being machined here in this example. Diamond turning of large off-axis paraboloid. Another view to form the free-form mirrors. So its applications lies in making the lenses. The lenses are made using these processes. So this was some of the examples of slow to servo process. Now fast to servo process, again the same thing. However, the vibrations which are given to the z-axis are of higher frequency as compared to the slow to servo process, and they can, this slow to fast to servo process can be used for the turning of functional surfaces which are having more complicated structures. So here we have a video graph which shows the fast to servo process. From the Perisitech. So here the RPM is currently low, 100 RPM, and the stroke of 4 mm with an acceleration of 0.1 g has been applied. Further, the RPM has been increased to 1200 RPM. Along with RPM, the acceleration has been increased to 12.9 g. A slow motion video shows the machining of fast to servo process with 10,000 frames per second. What are the various applications which we can have? We can fabricate various type of functional surfaces using diamond tool, single diamond tool machining process. Some of the surfaces are shown in this video graph. This is an elliptical Fresnel mirror. Now we are fabricating one toric surface. This is a toric surface here. And if we have the X and Y axis both available in the system, we can make this type of symmetrical surfaces with various contours. So here a lens array has been fabricated on a square shaped surface. Various pyramids are formed on the surface. Here the aluminum has been machined to form a convex type of machine. We can do the machining on plastic also. So these are some of the examples of the capability of the machine. Okay. So in the last few slides, we have seen some of the capabilities of the machine. The machine has very vast capabilities, and they have a wide range of application in the field of optics, in the field of semiconductors. Here, our challenge is to produce the nanostructures on the magnesium alloys using the diamond turning machining. However, there are some big challenges in the machining of magnesium alloys. First challenge, as we all know, magnesium catches fire easily. So it is highly flammable material. So people generally does not operate magnesium materials over the DTM machines. So chip ignition and fire hazard is one of the issue here. So flammability, magnesium chips are highly flammable and can ignite during machining, especially in dry conditions. Hydrogen generation happens. Safety measures are some of the issues in high speed machining. Tool life and built up edge formation happens because magnesium is highly ductile material, and the chips which are formed adhere on the tool material, which further deteriorate the surface of the machine, and tool wear is also one of the issue. Surface quality is very poor in machining of magnesium. If we use any machine in conventional machining methods or micro machining methods, we will get very poor surface quality. Surface defects will be there. Corrosion and coolant issues will be there. So magnesium alloys has inherent low corrosion resistant, and any imperfection or damage to the machine surface can make them more susceptible to the pitting corrosion. So these are some of the challenges in the machining of magnesium. Another challenge is to select a proper tool and its geometry. So the tool and geometry can be understood in the terms of one parameter, which is relative tool sharpness. So relative tool sharpness is ratio of uncut chip thickness. You can see those who are from the mechanical background can understand what is uncut chip thickness. So this is the uncut chip thickness. And if this is the tool, then we can say this R is the tool radius. So if we take the ratio of A divided by R, it gives the relative tool sharpness. So if the uncut chip thickness or feeds are in the range of the tool edge radius, our relative tool sharpness will become unity. And here during cutting process we will get the cutting due to shearing process. If we decrease the relative tool sharpness, the process of cutting changes from shearing to extrusion. So what will happen when it is changing from shearing to extrusion? The shear angle or the angle of the repose changes. Here you can see the change angle of repose is positive. It changes at around 0.4 to negative, and the process changes from shear to extrusion, which deteriorate the surface quality. Further, if we reduce the tool sharpness angle by reducing the uncut chip thickness, we cannot change the edge radius, but we can change the uncut chip thickness. The mechanism will convert from extrusion to ploughing, and machining will not take place, but the bulging will take place on the material, and the the angle of ploughing will keep on decreasing. Further reducing of the tool sharpness angle in the range of less than 0.2 by further reducing the uncut chip thickness, the mechanism will turn from extrusion to ploughing to rubbing only, and tool will only rub on the material. It will not produce the desired machining effect. So in order to get the desired unchip thickness level and maintain the relative tool sharpness ratio, we have to select the tool edge radius based on the calculation as shown by the Professor Rahman and his team in this diagram. So we have done some of the literature review and find that for machining of AZ31B magnesium alloy, people have used tool radius of 0.9 micrometer for pre-machining, 0.5 for texturing, and 0.2 for sawtooth type of profile formation. These are the manufacturers of the tool. Here in another paper, people have used machining of magnesium AZ31, AZ61 and 91. They used the radius of 0.8 mm and a rack angle of 0 degree. In another one, Sumoto cubic boron nitride insert were used, and these are some of the angles. You can refer to the slide to find the, 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 the range of tools which can be used for machining of magnesium alloys. Here we have seen we have shown one of the tool. Here you can see the diamond insert is there, and the top view is shown here. This is our tool holder, and a machining video of machining of AZ31B magnesium alloy using this diamond insert is shown here. So we have tried various type of tools. We have tried polycrystalline tool. We have tried cubic boron nitride tool. Because of course the natural diamond tools are very costly to fabricate and very costly to use. So there are alternate tools which can be used for the process. Now I am showing some of the experimental details. These after lot of hit and trial pilot experiments, we reached these experiments. So we kept RPM of C axis around 1000. We changed the feed to 2 mm, 4 mm and 6 mm per minute. The depth of cut was 6 micrometers. The tool materials which were used was polycrystalline diamond. The shape was 55-degree diamond shape. Nose radius was used as 0.4 mm, 0 rack angle and 7-degree clearance angle. You can see here we have the magnesium AZ31B workpiece material. This is the vacuum chuck here. The PCD insert is here. Coolant has been flown through this nozzle and the tool post is shown. The The machine is from Precitech engineers. And then we measured the surface roughness and the optical profile through the white light interferometers. You can see the surface machined at 2 mm per minute, 4 mm per minute, 6 mm per minute. As we increase the feed rate, you can see the marks, rubbing marks or cutting marks are more visible on the surface. When the feed was kept at 2 mm per minute, the shallow grooves were observed on the surface along with the scratches and pits, and effect of material inclusions were also observed. After improving or increasing the feed rate at 4 mm per minute, the frequent scratches on the surfaces were seen, shallow grooves were evident, and mirror surface was achieved. And further increasing the feed rate, deep grooves on the outer surface was observed, scratches were observed, and the mirror surface was converted into clouded type of surface. So these are some of the one of the photograph of the machine samples. You can see if you see directly, it looks like a mirror polished surface, but at the micro level, it gives us the things which are happening in the material. So in at 6 mm per minute, you can see the surface got some of the clouded type of thing. So the surface roughness was measured, and it was found that the highest surface roughness was with the lowest feed rate, and with an increase in feed rate, the surface roughness was improved, and a sharp decrement in the surface roughness values as the feed rate increases from 2 to 4 mm is observed, and this can be related to the absence of pits and voids observed at the lower feed rates. The surface roughness values increases further when we increase from 4 mm per minute to 6 mm per minute. And again, this is related to the deep scratches developed on the surfaces due to the adhesion between the workpiece material and the cutting tool. Constant spindle speed is used, which suggests that the cutting speed is not constant. So if you come from outside to the center, the linear velocity of cutting changes. So this is shown by measuring the surface roughness near center, middle of the surface, and extreme end of the surface. So the lowest value of the surface roughness was at the extreme end when the feed rate is 4 mm per minute, which indicates that the surface generation mechanism is dependent on the combination of both feed and the cutting speed. The lowest value of RA was obtained to be 164 nanometers, which is still not good as per the capability of the diamond turning process, but this is the best which can be achieved on the magnesium alloy surface. Now, after getting the best parameters, we try to fabricate the micro lens arrays on the workpiece surface to get the super hydrophobicity on the surface. So this is the methodology of the work. That first we have programmed the machining process to produce the 3D lenslet surfaces. The surface setup was done. Design and surface options were created. Parameters were set from the previous study, and then the spacing and radius of the parameters or the pits lengths were set. So you can see these are the micro lens. We created the convex lens as well as the concave lens. We used the drive machining condition as well as the lubrication condition, and we varied the pitch between the two lens as well as the diameter of the lenses, and this h is the depth at which the lenses are created. These are the optical images of the machine surface. You can see the concave lenses are shown here as the micro lens arrays, and here we can see the convex type of lenses over this part, and then we can see these are the coarse micro lens arrays produced on the surface of the magnesium alloy, and the fine micro lens arrays produced on the surface of the magnesium alloy. After that, we tested them on the optical tensiometer to find the the contact angle measurement. We have in general the Young's models where the contact happens between a solid and a liquid surface, and the energy is used to find the nature of contact happening there. If we create some of the surfaces like this, it can have a Wenzel type of model where the liquid penetrates inside the material, or it can have the Casey-Baxter type of model where it does not penetrate inside the surface. So air pockets field gets inside the hollow surface, and the liquid droplets lie over the surface. So these are some of the results which we got, and these are for the 0.8 mm and 0.4 mm diameter of micro arrays. So you can see these diameters. The diameters are 0.8 and 0.4 mm micro. The pitch of these arrays were 1.5 times the diameter. The conditions used were the dry condition as well as the wet condition. So a contact angle was achieved of around more than 90 degrees. So for the wet condition, when the diameter of the lens slit was 0.4 mm. So by creating these lens slit surfaces over the implant surfaces, we can increase the non-contacting behavior, which ultimately decreases the corrosion degradation of the material and improves the implant life. This is the summary that the best roughness which was achieved in this work was around 164 nanometers at a feed rate of 4 mm per minute, and then the surfaces were produced in the form of micro lens, and a contact angle of near around 100 degrees was obtained uh, in the work. A lot of results are there. I didn't want to bombard all of you with the all of the results. So I have just presented some of the important results. Um, Rest of the results will be published in the near future. And with this, I stop with my presentation. And if you have any question, you can ask.
Yes, sir.
Sir.
In chat box, Dr. Joshi, in
Yes, sir.
chat box, Venkataraman sir has asked something. He
Okay.
said he is asking the plastic lenses are polycarbonate and PMMA. What else can be machines? In chat box, you also can see.
No, I'm trying to maximize it. Let me see. Will it be feasible to use calcium for creating bone-like structures using additive manufacturing in near future? The additive manufacturing has some of the limitations. One, we have to see the properties like the burning effect. So calcium melting point has to be seen. What people used to do is people used to coat the calcium coatings like hydroxyapatite coatings and calcium carbonate coating. These are some of the coatings. People coat this using laser melting. So that is one of the way of additive manufacturing. That is not the standard additive manufacturing or 3D printing as per the definition. but people have used those techniques. I am not sure about the direct fabrication of bones using calcium. I have to explore in this way. Another question is, can diamond texturing be used for surface texturing? Yes, diamond texturing can be used for surface texturing, but we need more axis, as can be seen in the diagram. So let me again go to the picture of the machine. Just 2 minutes. So here we can do texturing. So x-axis you can move like this, but if you have the capability of moving in the y-axis, so a lot of machine does not comes with the capability of y. If you purchase the machines with the capability of y-axis movement, the cost of machine again improves a lot, which goes out of the budget. But if you have the machine which has the capability of having moving this workpiece table in the y-axis, and fast tool servo facility is there, different type of texturing shapes can be produced. Okay, sir. I can. Okay, plastic lenses are polycarbonate and PMMA. What else can be machined? Plastic lenses can be machined apart from plastic, hard to machine materials like the brittle material. Silicon is one of the brittle material, and it is not machined easily using the conventional process. The ductile mode machining of silicon has been possible using the diamond turning machining. Uh, we can machine hard materials like titanium. People have explored those. And even softer materials like coppers, they are again very challenging to machine over this surface. Glass is one of the material which can be machined using the, again in the ductile, which is a brittle material and can be machined in the ductile mode. Yes, sir. Uh, any more question, or was my answer satisfactory?
Is there any other question?
So the machining facility is available here at IIT Bombay Machine Tool Lab. If anyone wants to use the facility here, they can contact Professor Rakesh Mote and use the facility.
Okay, sir. If there is no questions from the participant, then I would like to thank to you for delivering and sharing your research work with all of us. And with this, let us end up our session. Thank you very much, Dr. Joshi.
Thank you, Piyush sir. Thank you for inviting me and giving me opportunity to discuss the work in front of this many beautiful audience. Still listening to the technical talks till late night, 9 p.m. Empty stomach. So I appreciate the participants and your hard work, sir.
Thank you. Thank you. And good night to all of you. So now we can disconnect the meeting. Thank you very much. Thank you
Thank
to
you.
all. Tomorrow we are going to meet at 6 o'clock sharp evening.
Thank you, sir.